What would happen if oxygen disappeared from Earth for just 5 seconds?
I mean, it sounds like a totally ridiculous hypothetical,
Yeah,
right?
exactly. You'd think, well, just hold your breath for 5 seconds. No big deal.
Right. I mean, anyone can hold their breath for 5 seconds.
But if oxygen actually vanished from the planet for that tiny window of time, I mean, the world as you know it would instantly collapse.
Oh, completely. It would be apocalyptic.
The daytime sky would turn almost black, right? Because oxygen particles are what scatter blue light.
Yeah. And every piece of untreated metal would instantly cold weld itself to any other metal it touched.
Which is wild, because that microscopic layer of oxidation that keeps them apart, that would just be gone.
And the ground beneath your feet, the Earth's crust is actually packed with oxygen, so it would just crumble.
Like a global freefall. We rarely think about this invisible gas effortlessly flowing in and out of our lungs. But today, we are going to change that. Welcome to our deep dive into the complete epic story of oxygen. Element 8.
It is so remarkably easy to take for granted because we can't see it or taste it or smell it.
Right, we just intuitively know it keeps us alive.
Exactly. But framing oxygen merely as, the air we breathe, it completely misses the scale of its influence.
It really does.
It is one of the most powerful, dynamic forces shaping not only our planet, but the entire universe. I mean, it acts as a creator, a destroyer, and basically the ultimate enabler of biological and chemical complexity.
So our mission today is to trace that incredible influence. We are taking you on a journey spanning billions of years, starting from its origins in the explosive deaths of ancient stars.
Down into the microscopic engines inside your own cells.
Yeah, and finally out to the cutting-edge technology that will one day carry humanity to Mars.
To really understand oxygen's fundamental nature, we have to go back to a time long before the Earth even existed.
Right, setting the stage.
Yeah, so following the Big Bang, the early universe didn't have any oxygen at all.
Really? None.
None. It was essentially just this massive swirling soup of the simplest, lightest elements. Just hydrogen and helium.
Okay, hold on. Let's trace that back. If the universe started with literally just hydrogen and helium, where did the actual physical oxygen atoms currently sitting in my lungs come from?
They were forged, literally forged in the extreme furnaces of ancient, massive stars.
Oh, wow.
Yeah, deep inside a stellar core, the pressure and temperature are so unimaginably high that atomic nuclei are forced to smash together and fuse.
So it's like a cosmic pressure cooker.
Exactly. And over millions of years, these stars fused hydrogen into helium, and then eventually the immense gravity forced the helium and carbon to fuse together, creating an entirely new, heavier element, oxygen.
Wait, so if it's forged in the absolute center of a star, how is it floating around my living room right now? Because stars are incredibly dense, right? Stuff doesn't just casually leak out of a stellar core.
No, it doesn't leak. It requires the star to completely self-destruct.
Ah, so a violent exit.
Very. When these massive ancient stars exhausted their nuclear fuel, they couldn't support their own weight anymore. They collapsed inward at a fraction of the speed of light.
That is, I can't even fathom that speed.
It's insane. And then they rebounded in a spectacular explosion, a supernova.
Right.
And that colossal detonation is the only event violent enough to scatter the newly minted oxygen, along with other heavy elements, out into the cosmic void.
So it blasts it everywhere.
Blasts it everywhere. And over billions of years, those scattered clouds of star stuff coalesced to form new planetary systems, including ours.
Okay, so the literal atoms in my lungs right now, the ones keeping me alive as I speak, are the scattered ghosts of detonated stars.
That is exactly what they are.
That is deeply unsettling and completely mind-blowing at the same time. But, I mean, it took humans centuries to figure any of this out, right? We operated for a long time on the assumption that air was just one indivisible thing.
Oh, yeah. Humanity was stuck on the ancient philosophy of earth, water, air, and fire for millennia. We didn't know air had parts.
Right, it was just air.
Exactly. The scientific revolution finally cracked the code in the late 1700s, though. A few chemists, like Carl Wilhelm Scheele and Joseph Priestley, they isolated oxygen gas, but they didn't really grasp what they had.
So who actually figured it out?
It was the French chemist, Antoine Lavoisier. He was the one who finally identified it as a unique, highly reactive element.
You know, I always hear Lavoisier cited as the father of modern chemistry, but what did he actually do? Because before him, people believed in this mystical substance called phlogiston.
Phlogiston, yeah.
Right, and they thought that was what made things burn and released into the air. How did he prove them wrong?
Well, he used meticulous measurement to prove that mass is conserved. He basically took a carefully weighed amount of liquid mercury and sealed it inside a glass vessel that just contained normal air.
Normal air, sealed tight.
Right. Then he heated the vessel for several days. And he noticed these red flakes of a new substance forming on the surface of the mercury.
Flakes just appearing out of nowhere.
Well, seemingly. But when he weighed the remaining air inside the vessel, he found the air had actually lost mass.
Ah.
And importantly, that leftover air could no longer support a flame or keep a mouse alive.
Because the oxygen in the trapped air had bonded with the mercury?
Exactly. He then collected those red flakes, which we now know as mercuric oxide, and he heated them at an even higher temperature.
What happened then?
The flakes turned back into liquid mercury, and they released a gas.
Let me guess. The gas weighed exactly the same amount.
Perfect match. When he weighed that gas, its mass perfectly matched the mass that had vanished from the air in the first experiment.
Wow. So it wasn't magic.
No magic. He proved burning wasn't about an object releasing some mystical fire element. Burning was an object aggressively capturing this new gas. He named it oxygen.
And in doing so, he kind of birthed the entire field of chemistry, right? By showing the world is made of interacting elements.
Yeah, that was a big paradigm shift.
So, to understand why Lavoisier saw oxygen aggressively capturing other metals, we really need to understand the mechanics of what it actually is. Element 8 on the periodic table.
Yeah, and the number 8 defines its entire personality, honestly.
Oh, so?
Well, an oxygen atom has 8 protons in its nucleus, surrounded by 8 electrons. And the arrangement of those electrons dictates everything it does.
Because atoms want to be stable, right?
Right. Atoms generally seek chemical stability by having a full outer shell of electrons. Now, for oxygen, a full outer shell requires 8 electrons, but it only naturally has 6 in that outer layer.
So it's missing 2.
Missing 2.
Well, why does missing 2 make it so notoriously reactive? A lot of elements are missing electrons.
It comes down to a property called electronegativity.
Electronegativity.
Yeah. Because oxygen has 8 positively charged protons in its nucleus, there's a very strong magnetic pole radiating outward. In atoms with more electron shells, that pole gets shielded.
Like layers of clothing blocking the heat.
Great analogy, yeah. But oxygen is small. Its 6 outer electrons don't shield that intense positive charge from the environment. So oxygen is incredibly hungry.
Hungry for electrons.
Famished. It exerts a massive pull to steal those 2 missing electrons from almost any other element it comes across, just to achieve stability.
Okay, so it's less of a social butterfly and more of like an atomic mugger.
I love that.
It's just walking around the periodic table, violently ripping electrons out of other molecules' pockets just to complete its own outer shell.
That is a highly accurate way to look at it, honestly. At room temperature, oxygen atoms won't even exist on their own.
Oh, really?
Yeah, they pair up with each other to form O2, sharing electrons to appease that hunger. That's the colorless gas we breathe.
But I'm guessing that partnership doesn't last if a better target comes along.
Not at all. The moment another weaker element comes along, oxygen will break its own O2 bond just to tear into the new element. This constant drive to steal and share electrons makes oxygen the ultimate engine of chemistry.
And that aggressive theft is exactly what created the foundation for life.
Well,
Water.
water, exactly.
Because that's just 2 simple hydrogen atoms basically getting bullied into sharing their single electrons with one extremely hungry oxygen atom to make H2O.
Yeah, without oxygen-specific electronegativity, water as we know it simply wouldn't exist. And without water, life on Earth never would have started.
But here's the paradox that always gets me. Early in Earth's history, life evolved in those oceans, right? But the atmosphere had almost no free oxygen in it.
None. It was dominated by nitrogen and carbon dioxide.
So how did we transition from a carbon dioxide atmosphere to the oxygen-rich air we have today? I mean, I know we usually credit trees and forests as the lungs of the earth.
And forests do their part today, sure.
Yeah.
But the heavy lifting started billions of years ago with these microscopic marine pioneers called cyanobacteria.
Cyanobacteria.
Yeah. They evolved a biological mechanism called photosynthesis. They basically used solar energy to force carbon dioxide and water to react, building sugars for food, and spitting out oxygen as a waste product.
So they were just dumping their trash into the atmosphere.
Basically. And over hundreds of millions of years, they pumped so much of this oxygen byproduct into the oceans and air that it caused what scientists literally call the oxygen catastrophe.
Wait, catastrophe? For an element that supports life? That sounds backward.
Well, for the anaerobic life forms that dominated the early Earth at the time, Oxygen was a highly toxic, corrosive pollutant.
Oh, because it rips electrons away from things.
Exactly. When cyanobacteria flooded the world with oxygen, it caused the first mass extinction on our planet. It wiped out almost everything.
Wow.
But, it cleared the stage for new types of life to evolve organisms that could actually harness that aggressive chemical power.
And we're the descendants of those survivors.
We are. And today, marine phytoplankton continue that legacy, producing over half the oxygen we breathe.
Breathing's another one of those things we totally oversimplify. We think of inflating our lungs like balloons, and we think that's the whole process.
Right, in and out.
Yeah, but the lungs are just the delivery system, handing the oxygen off to the bloodstream. The real work is cellular respiration.
Yes. Your cells use oxygen to relentlessly pull electrons away from glucose molecules, the food you eat.
So it's controlled tearing apart of glucose.
Precisely. When oxygen rips those molecular bonds open, it releases chemical energy. Your cells capture that energy to create a molecule called ATP, which is the biological fuel for everything from a heartbeat to firing a neuron.
Oxygen is literally the chemical spark plug for that microscopic engine.
That's a perfect way to phrase it.
So plants breathe out oxygen, we breathe it in to dismantle our food for energy, and we breathe out carbon dioxide, which the plants take back. It creates this loop that keeps our atmosphere at roughly 21% oxygen.
Roughly 21%, yeah.
What if that percentage shifts, though? If oxygen is our primary metabolic fuel, wouldn't say 35% oxygen make us run faster and think clearer, like a supercharger?
Actually, it would do the exact opposite. 21% is a very specific physiological constraint. If we push the atmosphere to 30 or 35%, things get disastrous fast.
Really? How so?
Let's look at insects, for example. Insects don't have lungs like we do. They breathe through a network of microscopic tubes called trachea, and the oxygen has to passively travel down these tubes.
Okay.
At 21% oxygen, the gas can only diffuse so deep before it's depleted, which puts a hard physical limit on bug size.
Oh, I see where this is going.
Yeah. At 35%, that richer oxygen pushes much deeper into the tissue, allowing the insect's body to scale up dramatically. We'd be dealing with dragonflies the size of hawks.
Which actually existed, right? In Earth's prehistoric past when oxygen levels were higher.
They absolutely did.
Okay, giant bugs are definitely bad, but what about human physiology?
For humans, breathing high concentrations of oxygen long-term causes massive cellular damage.
Because of that electronegative hunger.
Yes, that same hunger that breaks down your food would start breaking down your own proteins and DNA. Furthermore, at 30% concentration, the atmosphere becomes intensely flammable.
Oh, right.
A single lightning strike could ignite a global firestorm. Even wet, living vegetation would burn effortlessly.
So we really have this Goldilocks 21% balance that keeps us from either suffocating or bursting into flames.
Exactly.
But even at 21%, oxygen's relentless drive to steal electrons doesn't just stop. It just happens at different speeds, right? Fast electron stealing is a fire. But what happens when it steals electrons in slow motion?
When oxygen steals in slow motion from metals at normal temperatures, we get rust and corrosion.
Right.
Think about the frame of the car sitting in your driveway right now. There is a silent microscopic war happening on the bumper where oxygen from the morning dew is literally prying iron atoms apart.
Just ripping them away.
Yeah, it pulls electrons away, altering the atomic structure of the metal, turning strong, solid iron into weak, flaky iron oxide.
It's just chewing through our infrastructure. And fire is the exact same process, just sped up.
Fire is rapid oxidation. You need fuel, heat, and oxygen.
Let me clarify something here because this is a huge misconception. Oxygen itself isn't actually flammable, right? If you light a match in a room of pure oxygen, the air itself doesn't catch on fire.
No, it does not. Oxygen is the oxidizer. It's the enabler.
The enabler.
Right. When you apply heat, you give the oxygen molecules enough energy to break apart. Those newly freed, ravenously hungry oxygen atoms aggressively attack the fuel. They rapidly tear its carbon and hydrogen bonds apart to steal electrons.
And that violent tearing releases light and heat.
Exactly, which fuels a chain reaction. Oxygen doesn't burn. It facilitates the burning of other materials with terrifying efficiency.
So humanity realized we have this element that is a vital life giver, a slow degrader of metal, and a terrifying enabler of fire. And instead of just existing with it, we started bottling it.
We did. We harnessed that reactive power to push the boundaries of extreme environments.
Like in medicine.
Oh, isolated pure oxygen is one of our most critical medical tools. In intensive care units, emergency rooms, and during surgeries, supplying concentrated oxygen can keep a patient's vital organs functioning when their own lungs or heart are failing to deliver it fast enough.
And what about those hyperbaric chambers?
Yeah, we use hyperbaric oxygen chambers, pumping high-pressure, pure oxygen into the body to rapidly treat decompression sickness for scuba divers, or even heal deep tissue wounds.
It also lets us explore environments where we have no biological business being.
Right.
Scuba divers carry compressed air to explore the ocean floor. High-altitude aviators and fighter pilots rely on onboard oxygen generation systems so they don't black out in the thin upper atmosphere.
Hmm.
But, I mean, the ultimate extreme environment is space.
Absolutely.
There is no oxygen in the vacuum of space to keep rocket fuel burning.
And when you are launching thousands of tons of metal into orbit, you need an unimaginably powerful continuous fire to break the grip of Earth's gravity.
So how do they do it?
Rocket engineers take pure oxygen gas and chill it down to minus 297 degrees Fahrenheit.
Minus 297.
Yes. At that extreme temperature, the physical mechanics change. The oxygen condenses into a dense pale blue liquid known as LOX, or liquid oxygen.
Why go through the trouble of making it liquid, though?
Volume. A gas takes up way too much space. By condensing it into a liquid, you can pack a massive amount of oxidizer into the rocket's tanks. They pump this liquid oxygen into a combustion chamber alongside rocket fuel to create a controlled explosion.
Oh, I see.
The oxygen forces the fuel to burn at a rate that wouldn't be possible with normal atmospheric air.
The scale of that is incredible. The exact same invisible gas keeping the cells in my brain alive right now is being super chilled to blast spacecraft into orbit.
It is wild.
And we use it for heavy industry too, right?
Heavy industry relies on it completely. They blast pure oxygen gas into furnaces to burn away carbon impurities and iron, which is how we forge the high-strength steel used in skyscrapers.
Oh, really?
Yeah. And welders mix pure oxygen with acetylene gas to create a flame hot enough to slice right through thick metal plating. We even pump massive amounts of oxygen into wastewater treatment plants.
To clean the water.
Exactly. It supercharges the metabolism of the bacteria that eat the waste, cleaning our drinking water at an industrial scale.
Wow. You know, with an element this ubiquitous, there are always pervasive myths that need clearing up. You mentioned earlier that breathing pure oxygen long-term is dangerous, but pop culture really pushes the idea that more oxygen is always better.
Oh, definitely.
You see oxygen bars and oxygen facials marketing this idea that pure oxygen will make you superhuman or, like, cure a hangover.
Yeah, that's a dangerous misconception. Scientifically, the human body is optimized for 21% oxygen. When you introduce too much oxygen into a healthy system, you overwhelm your cell's ability to process it cleanly.
Which does what?
It creates an excess of what we call free radicals.
Which are basically oxygen atoms that have lost an electron and are desperately trying to replace it.
Yes. These unstable free radicals will violently steal electrons from anywhere they can, including your own healthy cell membranes, your DNA, and your central nervous system.
That sounds really bad.
It is. This causes oxidative stress. Over time, oxidative stress accelerates cellular aging, and acute exposure to high-pressure pure oxygen can actually cause central nervous system toxicity, leading to seizures.
So your body knows exactly how to handle 21%. Pushing it higher doesn't supercharge you. It slowly breaks you down.
It literally breaks you apart at the cellular level.
Okay, here's a fact that absolutely shifted my perspective.
Okay.
We think of oxygen primarily as a gas floating in the sky. But the atmosphere isn't actually where most of Earth's oxygen is stored.
Not even close. Oxygen is the most abundant element in the Earth's solid crust.
The crust.
Yeah. By weight, nearly 47% of the rocks, dirt, and sand beneath your feet is made of oxygen.
How does an invisible gas make up half the mass of a solid rock? That doesn't even make sense.
It goes back to that intense electronegativity. Billions of years ago, when the Earth was a molten ball forming and cooling, the oxygen aggressively bonded with elements like silicon, aluminum, and iron.
Oh, it grabbed them while they were hot.
Exactly. It pulled their electrons, locking itself into solid, stable mineral structures called silicates and oxides. The quartz and sand, the granite and mountains, they are fundamentally oxygen compounds.
So you are walking on billions of tons of trapped, crystallized oxygen every single day.
Every single day.
That structural locking is fascinating.
Mm.
And it bridges perfectly into the future, actually. We've mastered how to extract and use oxygen here on Earth. But the next frontier of technology is focused on how we manufacture it for interplanetary survival.
Absolutely.
If we want to build a permanent base on the moon or send astronauts to Mars, We can't afford the weight of shipping heavy tanks of liquid oxygen millions of miles.
No, the logistics of that are impossible. The future of space exploration relies on in situ resource utilization.
Basically living off the land.
Right. On the International Space Station, they use solar electricity to split the recycled water from astronaut sweat and urine back into hydrogen and oxygen.
Gross, but effective.
Very effective. But for Mars, engineers are developing technology to manufacture oxygen directly from a completely hostile atmosphere.
And the MOXIE experiment on the Perseverance rover is doing exactly this, right?
Yes, the MOXIE device is incredible. The Martian atmosphere is incredibly thin and mostly composed of toxic carbon dioxide. A MOXIE takes that carbon dioxide, which is one carbon atom bonded to two oxygen atoms, and uses intense heat, around 1500 degrees Fahrenheit, along with an electric current, to forcibly rip an oxygen atom away from the carbon.
Just tearing it right off.
It literally breathes in unbreathable Martian air and pumps out pure oxygen gas. It is a working proof of concept for the massive industrial oxygen generators we will need to sustain human habitats and refuel rockets for the journey back to Earth.
I love that. We're taking the very element that shaped our biology and our home planet, and we're engineering it to be the literal key to surviving on alien worlds.
The story of oxygen is a story of total transformation. It really is.
Let's look back at the scale of what we've covered today. We started in the absolute vastness of the cosmos, where the violent deaths of giant stars forged the first atoms of element 8. Those atoms drifted through space, coalescing to form the Earth, where they locked themselves into solid bedrock. Then, microscopic life figured out how to harness sunlight to pump that oxygen into the air, triggering a mass extinction, but ultimately re-engineering our atmosphere and setting the stage for complex life.
Our entire biology is built around this incredibly hungry, reactive element. We use its magnetic pole for electrons to unlock the energy in our food. We use its aggressive nature to forge steel, treat the critically ill, and power our rockets. Oxygen is the fundamental cosmic spark that makes complexity possible.
The next time you take a deep breath, consider the ancient supernova that forged those specific atoms currently binding to your red blood cells. If the invisible air in your lungs has such an epic, violent billion-year history, what other unseen forces are quietly shaping your reality right this very second?